In this video, we're going to look at how to convert back and forth between moles and the number of atoms or molecules that we have. Now, when we do conversions like this, atoms and molecules are sometimes both referred to as particles. A particle is just a word for any individual thing. So a particle could be a jelly bean, or a coin, or a paper clip, or an atom, or a molecule. So we'll work through problems like this, where we have to go from moles to, say, atoms, or we have to go from atoms and convert back to moles. Okay, so here's our first question. For each one of these problems, I'm going to do it two ways. First, I'm going to show you how to think through it in kind of a simple, straightforward way so you can really understand what you're doing. Then, I'm going to show you how to use conversion factors. I think conversion factors don't always make a lot of sense, and I know a lot of students are confused by them, but teachers and textbooks tend to really like conversion factors, so it's important to know how to solve questions like this using conversion factors too. Okay, so how many atoms are in 5.5 moles of atoms? We're talking about moles and atoms here, so let's just refresh our memory about moles, okay? A mole is like a dozen, but there are 12 things in a dozen, and there are 602 hexillion things in a mole. We often abbreviate this super long number with all these zeros, 602 hexillion, as 6.02 times 10 to the 23rd. Moles can be a little bit tricky at first, and so I want to keep talking about the similarity to dozens as we work through this first problem, okay? We want to know how many atoms are in 5.5 moles of atoms, but to get a handle on how to think through this, let's first think about how we would do this kind of problem if we were talking about dozens instead of moles. So what if instead of 5.5 moles, we were talking about 5.5 dozen? Well, this math is probably pretty straightforward. There are 12 things in a dozen, so to figure out how many atoms are in 5.5 dozen, we take 5.5 and then we'd multiply it by 12, the number of things in one dozen, and that would tell us how many atoms or how many things are in 5.5 dozen, okay? But we're not talking about dozen here, we're talking about moles instead. So instead of multiplying this by 12, the number of things in a dozen, we're going to take 5.5 and we're going to multiply it by 602 hexillion, the number of things in one mole. Now, this big number here is a real pain with all these zeros, and if you're actually going to do this math, chances are you wouldn't want to use this long version here. You'd want to use the shorter version in scientific notation. So let's take this big number, 602 hexillion, and write it in the more manageable form of 6.02 times 10 to the 23rd. This is the same number as 602 hexillion. It's just an abbreviated version here. Okay, so you've written this out. Chances are you're going to use a calculator, a scientific calculator, or a graphing calculator to solve this problem. So here's how you're going to type it in. 5.5 times 6.02 E23. Yes, E23 is usually how we do exponents in a scientific calculator. The E is 10 to the exponent, and then 23 here is the exponent. Plug this into the calculator, and we're going to get this as our final answer. There are two things that I need to do to this answer. The first thing I need to do is sort of take it out of calculator scientific notation and put it into normal person scientific notation. So I'm going to write 3.311 E24 is 10 to the 24th. Okay, so now it's in regular person scientific notation, but the next thing that we got to do is take into account significant figures. Okay, we'll look at the numbers that went into this to figure out how to round it correctly. Okay, there are two significant figures in 5.5, and there are three significant figures in 6.02. So we're going to round this number to the lower number of significant figures. We're going to round it to 2. Okay, so we're going to take the 3, and we're going to take this 3, and then we're going to look at the 1 to figure out whether to round up or to keep it the same. It's a 1, it's lower than 5, so we keep it the same. We'll do 3.3 times 10 to the 24th, and what we're solving for here is atoms. This is our final answer. Now, so many people see a number like this, 3.3 times 10 to the 24th, and they don't think of it as a real number. So please keep in mind that this number is just a shorthand for this super, super long number with all these zeros. This is 3 heptillion, 300 hexillion atoms. Okay, so 3.3 times 10 to the 24th. It's not some weird Martian number. Keep in mind that it is just a shorthand version of this very long number here. And if for some reason your teacher doesn't let you use a calculator and you have to do this out by hand, I have another video on doing mole calculations by hand instead of a calculator, so you can check that out. So anyway, this is how we do this problem using the sort of simple, straightforward method. We multiply 5.5 by the number of things in 1 mole, plug it into the calculator, and this is what we get. Now let's look at how we could solve the same problem using conversion factors instead. Okay? In this case, we're going to be starting with this number here, 5.5 moles. 5.5 moles. And now, we are going to want to multiply this by a conversion factor that's going to get rid of moles and is going to give us atoms. To write this conversion factor, we're going to think about moles. Let's look at this definition up here. I want to rewrite this just as an equation with an equal sign, okay? So here we have 1 mole equals this much. I really haven't changed anything. But I put the equal sign in here because we use relationships like this with one thing on either side of an equal sign. We use relationships like this to write conversion factors. Okay? So here's how we'll take this relationship and write a conversion factor. A conversion factor has both a top and a bottom, and we take something on one side of the equation, 1 mole, and we can put it on, say, top of the conversion factor, and then the thing that's on the other side of the equal sign, we put that on the bottom. So I'll do 6.02 times 10 to the 23rd. Things here, but we're talking about atoms. And this conversion factor is just telling me that in 1 mole, there are 6.02 times 10 to the 23rd atoms. But for every equation like this with an equal sign, there are 2 conversion factors that we can write. We can write it like this, or we can flip it. That's cool too. So I could also write 6.02 times 10 to the 23rd atoms on top with 1 mole on the bottom. Now both of these conversion factors are totally valid. Which one do we want to use for this problem? Well, we want to multiply this by a conversion factor that's going to get rid of moles, is going to leave me with atoms. So moles is on top here. I'm going to want to choose the version of this conversion factor that's going to give me moles on the bottom, so they'll cancel out. So I'm going to use this one. And then I've got moles on the top here, cancel out. Moles on the bottom, cancel out here. And that's going to leave me with atoms. Okay? What's the math I'm going to do? I'm going to do 5.5 times 6.02 times 10 to the 23rd divided by 1. Now you might realize that dividing this number by 1 doesn't really change anything. So all the math we're really doing is just 5.5 times 6.02 times 10 to the 23rd, which is exactly what we did up here. So you could just type this into your calculator and get this as an answer. Or, which would be totally fine, you could decide that you want to put this whole conversion factor in, and you could type it in like this. 5.5 times, and then parentheses, 6.02 E23 divided by 1. Whichever one you type in, you are going to get the same number here, which in regular person scientific notation is going to look like this, and then we round it using sig figs to get this number here. Now once again, don't forget that 3.3 times 10 to the 24th is just an abbreviated version of this very long number of atoms here. Okay? So that's how we go from moles to, say, atoms. Now let's look at how to do problems in the other direction, from, say, atoms or molecules to number of moles. How many moles is 4.6 times 10 to the 24th sulfur atoms? Okay, check out this number. I just want to remind you that this isn't some weird Martian number, that this is just a shorthand abbreviation for this very long number with a whole bunch of zeros. As we did before, instead of jumping right to moles, let's sort of do this common sense approach where we think about what we would do if instead of moles, we were talking about dozen. If we want to know how many dozen this big number were, well, we'd recognize that there are 12 things in a dozen, and so we would divide this number by 12. 12 things in a dozen. We want to know how many times would 12 go into this number. Okay, so we're going to be dividing by the number of things in a dozen. But as before, we're not talking about dozens, we're talking about moles. So instead of dividing by the number of things in a dozen, we want to find out how many moles is this, so we are going to divide by the number of things in 1 mole. So we're going to divide by 602 hexillion. As before, you're probably not going to want to use these giant versions of each number with all these zeros. So this is where the scientific notation comes in handy. Let's rewrite this in scientific notation. Okay, we're going to do 4.6 times 10 to the 24th divided by 6.02 times 10 to the 23rd. Put this into the calculator, and you'll want to type it in like this, where we replace the 10 to the 24th with E24, or 10 to the 23rd with E23. Hit return, and we're going to get a number like this. Now, it's not in scientific notation, so we don't have to worry about that, but we are going to want to round this with significant figures. There are 2 significant figures here, 3 significant figures here, so we're going to round this to 2 significant figures. We're going to take the 7 and the 6, look next door to figure out whether we round up or keep it the same. It's a 4, so we keep it the same. And we're solving here for moles. It's going to be 7.6 moles of sulfur atoms are in this super huge number of sulfur atoms. Okay, I'm going to just slip it in right here. And now let's look at how we'd use conversion factors to solve this same problem. Okay? Here we're going to be starting with 4.6 times 10 to the 24th atoms. And we want to multiply this by a conversion factor that's going to get rid of atoms and is going to move me to moles. So let's look at the 2 conversion factors that we could write using this relationship here. Okay, the first one, let's put our line here. The first one is going to put 1 mole on top. 1 mole. We're talking about atoms here. So there are 6.02 times 10 to the 23rd atoms in 1 mole. Or we could write this other conversion factor where we put 6.02 times 10 to the 23rd atoms on top and 1 mole on the bottom. Which of these do we want to use? We want to use the one that is going to get rid of atoms. Atoms is on the top up here, it's on the bottom here, so they're going to cancel out. Okay? Get rid of this, get rid of this. And now what's the math we're going to do? The math is going to be 4.6 times 10 to the 24th times 1 divided by 6.02 times 10 to the 23rd. Now, multiplying this number by 1 isn't really going to change anything. So all we're really doing is we're taking this number and dividing it by this number. The exact same math that we did up here. But just as we did previously, if you would prefer to put this as a big fraction into the calculator, that's totally cool too. It's going to look like this. 4.6 E24 times this whole fraction, 1 divided by 6.02 times 10 to the 23rd. But all you're doing is just dividing this by this, because this 1 doesn't really matter. We're going to get the same number here, which rounds to 7.6 moles. So that's how we go from a number of things like atoms, molecules, jelly beans, or coins to figure out how many moles are in it. We divide it by the number of things in 1 mole. Okay, so if you want some more practice with these kind of problems, check out the next video, Converting Between Moles, Atoms, and Molecules, Part 2.